Ladies and gentlemen, good morning. Welcome to Hong Kong and welcome to the Crouch Advanced Study Institute on the new materials and new concepts for controlling light and waves. I'm C.T. Chen from Hong Kong. Let me welcome you first. And it's our great honor to have our Provost, Professor Shyy, to say a few words to welcome everybody. So, Provost, please.
Well, good morning. It's my honor to be here. It's not your honor. Okay, let me make that clear. And of course, I'd like to extend you a very warm welcome on behalf of the university to come to HKUST. Many of you are one of our colleagues and students, but I know about 50 of you are coming from elsewhere. Of course, some of you have been here many times, but still, I think this is a good day. It's October now, and outside is not as humid, so. But please don't stay outside for too long during the regular workshop session, okay? As I understand, this is advanced study institute sponsored by the Croucher Foundation on new materials and the new concept for controlling light and the waves. I'm not in physics field myself. I'm an aerospace engineer. But certainly the topic is of a lot of interest to me as a layperson in a way, okay, in my field, of course, we talk about stealth fighter, F-117, and the B-2. And I remember once I was sitting next to Professor C.T. Chen and listening to one of his short presentation on this topic. That was my first question. Maybe we are out of business. We do not need, I think, Pratt & Whitney or Boeing, Lockheed Martin to design this kind of fancy gadget anymore. If we can get this one to work, okay. The other one, of course, is I look forward to seeing similar kind of skit in the future James Bond and the Star Wars movies. And I think these are all kind of things to me, certainly that invoke a lot of curiosity. I think certainly from a scientific point, even I can understand that it is fascinating to try to use photonic crystals, I think, which has a lot to do with Professor Yablonovich, who's sitting right there, one of our members of the IAS, and Professor John Pendry, who has done a lot of metamaterials work. Okay, and I think we have some of these founding scientists and pioneers sitting here. That also shows the quality of the workshop. I also understand that there are about 150 registrants in this workshop. Considering that Hong Kong has a population of about 7 million, if we extrapolate, not linearly, but in some way to compare to the US size, I think the similar conference or workshop in the US should have probably 10,000 people. Okay, so I think this kind of gathering I will only see in the computer trade show, okay, not for this kind of a scientific gathering. So also that shows, I think, in Hong Kong, even though it's a small city, in terms of population, it's very crowded, but still a small place. The curiosity and the scientific pursuit and the academic standard certainly is very clear. Okay, and that is, I think, in a way, why and how HKUST was established about 21 years ago. I think with a kind of dream to do something in science and engineering. Of course, nobody's perfect. We have to do business also. Okay. And so basically, 1 year later, I think we really have some very, very outstanding faculty members and the students. Okay, and as someone who has come here only just about 2 years ago, I claim no credit. I have to say I have a lot of appreciation and respect to what many of the colleagues before me have done. So without any further ado, I'd just like to say a few things about appreciation. First of all, of course, this is sponsored by the Croucher Foundation. And to me, Croucher plays a very, very unusual role in Hong Kong. It's basically, outside the Hong Kong government, the only foundation devoted to advancement of science, natural science, technology, and medicine. Okay, and in that sense, considering again the size of Hong Kong, Croucher's impact has been tremendous. Okay, we have seen Croucher's sponsorship and impact in many, many different occasions. And I think the size also plays to its advantage. So I can say that certainly we have benefited not only in this particular advanced study institute, but in many different occasions. I think this is something I certainly would like to thank CrowdStrike on behalf of my colleagues. The second thing certainly is the Institute for Advanced Study, which is our host for this particular, I think, study institute. And as you know, the Institute for Advanced Studies was established several years ago. And the goal was very simple, to advance scientific research to prepare Hong Kong to the highest caliber possible. And we have the honor of hosting the IAS here. The new building is going to be completed within the next few months. And certainly I would like to welcome you back in due time to see the very nice, very conducive environment. Maybe the next workshop on a similar or related topic would be really nice. It's literally on top of the hill. If you go to the other side of the bay, you can see this really commands the high ground of the HKUST. Okay, so we basically, it's almost like we're going up here to see Moses. Okay, so but IS being the sponsor of this workshop and many others, we also have a lot of different distinguished lectures, and we have some of the members of visiting members of IAS. Okay, some of you are sitting here. I think all these are meant for advancing all of our regular academic programs, not just to do it by itself. Okay, so in that sense, it is certainly very good, to say the least, to see that many of our faculty members and the graduate students from HKUST and the other sister institutions are here to share the experience and to really exchange ideas. Okay, and I also understand that we have some editorial colleagues from several leading journals here, and I certainly welcome you to observe, to also share your insight with us, and I look forward to learning a few things from you all. Thank you very much.
Yeah. So I think before we start with Professor Pendry's lecture, let me just say a few words of before we start. Again, I really appreciate the speakers who come from USA and Europe and Australia to come to teach us something new about this topic. And in particular, I'm very grateful for 7 of the speakers who is willing to speak a bit longer. We are very lucky to have the sponsorship of the CrowdStrike Foundation, which, as Prof have said, is the only private foundation in Hong Kong which is really committing resources to support research in Hong Kong for the advancement of science. But this foundation also has its own way of doing things, so we have very specific requirements to see how things should be done, and therefore some lectures are required to be at least of a certain duration, and that's why the way the conference is organized in this way. I would like to also take this opportunity to thank Professor Pendry in particular, who actually had initiated this activity, and without his help, I don't think we can have the opportunity to get so many distinguished speakers from all over the world. And I'm also very fortunate to have the assistance of the staff of IAS, and in particular, Mr. Linus C. And if you see Linus' email, this is Mr. C. Okay, and he helped us a lot. I think we should give him a big hand. And also other staff under leadership of Catherine, who's a senior manager of IAS, have helped us a lot. And a lot of you have asked me, why don't you organize the conference or this ASI in October? The reason is, in fact, a lot to do with the IAS building. We are supposed to have a beautiful building up the hill that should be ready for occupancy in August. And so this is supposed to be the major activity to celebrate the opening of the building. And initially we thought that if they promise us the building available in August, usually a bit, you have to have a safety factor, right? And so August is not safe, so make it to October. But due to a lot of unseeable, events happening, we are still here. Okay, so but it's not too bad. Okay, to have it here. Okay, and I have to apologize to a lot of the participant here is that for those of us who know about Hong Kong, we have very strict rules about food. And therefore, due to a lot of restrictions, we have not been able to provide lunch for everyone. And I apologize for that, okay? But for those of you who are local and who happens that we are not able to entertain you in the restaurant, please find some HKUST people and they will tell you where to get food for lunch, okay? And I know that everyone cannot go without the internet. And in fact, in the book, conference program book, near the last page, and in fact on page 87, there is instruction on how you can use internet. Okay, and there. Okay, and so Anna, you have something to say? Okay, then without further ado, may I invite Dr. Osborne to chair the first session. Okay.
So good morning and welcome to this symposium. This is the first session. And we have one tutorial from Professor Sir John Pendry. So I think we should just hand over to Sir John and he can begin his tutorial.
Yeah, thanks, Ian. Yes, good. Okay, well, thank you for your patience. It's an honor to be kicking off this conference in this spectacular location. When the mist clears, I'm sure you'll be able to see the wonderful bay down there. Since I have 90 minutes, I've split my talk into three pieces actually. The first bit will be introduction of background material on transformation optics, and then I'll talk about some new experimental results on transformation optics, and finally I will move on to talking about the application of transformation optics to plasmonic systems and the harvesting of light. So I can organize my notes here. That's better? Yes, I was deafening everybody. I'm sorry. So what is transformation optics? Well, very often in designing scientific instruments these days, we still use Snell's law. And Snell's law is still around after hundreds and hundreds of years because it gives you a very intuitive picture of how light works. It talks in terms of rays of light, which you can think of as streams of particles, and in your mind's eye you can follow, this is very gloomy, isn't it? Moving down. In your mind's eye you can follow the trajectories of those particles as described by Snell's law, essentially changing direction at interfaces. But if you want to work in the near field, and if we're doing plasmonics or we're dealing with static fields, then you do, and rays have absolutely nothing to say about a situation where you have to look at the individual electric and magnetic components. And transformation optics addresses that question of how do we have a more precise formulation of the behavior of light when we want to look at light on all length scales, and the ray approximation isn't good enough. So we take a leaf out of Albert Einstein's book, and in his theory of relativity, he remarked that gravity changes geometry, and therefore gravity should bend light. And he reformulated Maxwell's equations in terms of his bent space, and he famously was proved right when Eddington showed that light from a star is refracted around the sun. And the formalism which Einstein used can be taken over directly when you have a situation where the refractive index of a medium varies. So if you're in a situation like this, and you take a space which is straight with a flat space, a zero vacuum, for example, a beam of light, or a field line going through vacuum, and you distort this coordinate system, then if you imagine that the field line is nailed to the coordinate system, then as you distort the space, so the trajectory of the field line changes. Now, if you want that field line to obey Maxwell's equations, then Einstein gives you a formalism which tells you what values of epsilon and mu you must adopt in order to steer that field line in that direction. And in contrast to Snell's law, which is only accurate at the level of the ray approximation, this applies to how all field lines move. Any conserved quantity in Maxwell's equations, the D field, the B field, and the pointing vector is directly analogous to a ray of light, of course. These all obey this rule of being nailed to the coordinate system. How this works in practice, you can easily see by considering this very simple instance and asking what the values of epsilon and mu must be in order that this situation here is obeyed. So what I'm going to do is to make the simplest transformation. I'm going to take the central segment here. This is a ray of light or a field line. In this case, it's a ray of light. And I'm going to compress the central section so that now the field line goes on a zigzag or the ray of light goes on a zigzag. And then I'm going to ask what values of epsilon and mu I must place in here in order that that is consistent with Maxwell's equations. Now, we recognize that epsilon and mu in here must be tensors because you've singled out this axis through compressing along that axis. There's no change in the incompressed regions, so epsilon and mu are unchanged outside the blue region. And also, epsilon and mu must have the same transformation properties because they appear on the same footing in Maxwell's equations. There's symmetry between epsilon and mu in Maxwell's equations. So I'm going to do two thought experiments. In one, I'm going to send my ray of light along the direction of the axis of compression, and it's got to cross this shorter region with the same phase change that it crossed the longer regions before. And therefore, we have to increase both epsilon and mu by the compression factor in order to change this. So epsilon and mu, normal to the direction of the propagation, must increase if you compress along that direction. And then if you do a different experiment and you send your beam of light in this direction, well, you've already decided what epsilon is going to be, the response to the electric field, but we don't know what the response to this magnetic field is. However, in this direction, the phase change must be the same as it was before compression, and therefore we have to cancel what happens to epsilon with what happens to mu, because the product, which determines the refractive index, must be the same. And therefore, along the direction of compression, epsilon and mu are decreased. So the general rule is that if you squash a bit of space, perpendicular to the squashing in both directions, epsilon and mu increase by the inverse of the squashing factor. Along the direction of compression, they decrease. And if you imagine mixing up a coordinate system in any way, that simple law will tell you at any point what epsilon and mu are. So we worked this out some time ago, and I was asked to give a talk at a meeting in San Antonio in the early 2000s, and I thought I'd ginger them up. So we set ourselves the task of hiding something. Now, the problem about hiding things and making them invisible is not that they should simply refuse to reflect light, because that's just conventional stealth. You need a pot of black paint to achieve that, and that's fine. But it's not enough to achieve invisibility, as this statue of Peter Pan, which is in Kensington Gardens, just north of my college, shows, because Peter still has his shadow at this stage. Peter Pan, you remember, is the little boy who lost his shadow. And so the challenge is to make something lose its shadow. And that is done in a very simple idea, but in order to realize that idea, you really need to have transformation optics, because the idea is that if you could steer rays of light or field lines, and I'll give you instances of both later on in the talk, if you could steer the field lines around that hidden object and then return them to their original paths on the other side, an observer here would just see the same rays as if that object wasn't there, and he wouldn't know about this chicane here, which they'd done. It's like a skier going round a tree, but still reaching his ultimate destination. So the advantage of this is you can hide an arbitrary object. The compensating layer does not need to change as the object change. This system is a non-resonant system, and it has some dispersion, but that leaves plenty of room for it to have quite a wide bandwidth. And the disadvantage, of course, is that you have an anisotropic medium here because you've compressed it, and you really need metamaterials in most cases to make that object. So that's the idea, but to realize it, you have to decide exactly what values of epsilon and mu are here. And you see that transformation optics is ideally suited to this challenge, because what you're doing is you're taking the whole of space inside this sphere and you're compressing it into this annulus here. You're not disturbing any of the field lines here, and therefore you don't have to change epsilon and mu here. All the changes are in here. And that transformation optics technology is just perfect for solving that problem. But we do need a continuously varying medium, and that is not often achieved. Sometimes you see it when you see these mirages, which are due to hot air with a continuous gradient of density, and therefore a continuous gradient of refractive index, and that will bend light, but of course in an uncontrolled way. But we want to do it in a controlled way. So there's what we need to do. We take the flat coordinate system, we define an outer sphere beyond which there is no distortion, and an inner sphere from which all the space must be removed. We compress the stuff into this annulus, and then we apply that formula I mentioned earlier to tell what the epsilon mu must be in this annulus. A very simple mathematical transformation will achieve this compression. There are other better ones which people have come up with later, but that was the first one we thought of. And here are the values of epsilon and mu. Epsilon along the radius, because it's compressed along the radius, epsilon is reduced in this direction. In the two angular directions, the values of epsilon and mu increase because the compression is normal to these directions. And this simple formula will give you the cloak. Metamaterials, I don't need to dwell on this because I presume that nearly everybody here knows what a metamaterial is. Just to recap, it's a material in which the properties are mainly due to the structure of that material rather than to its chemical composition. And metamaterials were used by the group at Duke University, David Smith's group, to construct the first metamaterial cloak. This is rather an old slide, as you can see. It's not to appear this November. It appeared in November 2006 in Science. I did say I was recapping. And here is are the elements of the metamaterial. You can see that they change their shape, and hence the values of mu, in this case, from the outer to the inner ring. And there are some details of the fine-tuning, which, what did Dave Shyy do that fine-tuning, Dave? Yes. Yeah, that Dave Shyy used to fine-tune the design. And here are the first data of a cloaking experiment. Here's what the theory would say would happen if you had a perfect realization of those parameters. And so here are the pointing vectors. Here are the wave fronts. you notice that nothing penetrates into this inner region here, and that merging from the far side of the cloak, the wavefronts and pointing vectors are exactly the same as they would have been had the cloak not been there, but there's this process of capturing the radiation and guiding it around clearly going on inside the cloak. Now, the experiment didn't have an exact realization of the parameters, and here's what the simulation says would happen if the experimental parameters were as we thought they were. And you can see things are a little bit wobbly. In particular, in the central region here, it would be like me taking my glasses off and seeing you guys a bit distorted as I look through them, but nevertheless, it would come through. And here's the experiment, and you can see there's a pretty good tie-up here. And the main function of capturing this light and steering it through the cloak and plane wavefronts emerging the other side came out of that experiment. There have been many experiments since then. Okay, so that's a recap. Now, some water will be very useful if you have some somewhere, please. The goal after that was to extend these experiments from the, thank you very much, from the experiments with radar waves, which were done at Duke, to the optical region of the spectrum. The problem there is that to design a metamaterial in the optical region of the spectrum is a much more complex procedure, because you have to operate on the nanoscale, the sub-wavelength scale, in order to make that work. And worse than that, the range of material parameters out of which you'll make the metamaterial is much more limited. And so Jensen Lee, some years ago now, set about designing a cloak which was simple enough in concept that it could be realized at optical frequencies. And the idea was as follows, that actually there are three ways you can hide something. One way of looking at the cloak, so here's a cloak, and one way of thinking of it is of it being a lens. Now, most lenses are designed to magnify an object, but it's perfectly possible to design a lens which will make an object seem very small. And this particular lens, which is a cloak, makes an object so small that it's invisible. Okay. So it's a lens which demagnifies things, and anything inside that inner cloak here appears so small that you can't see it. Now, there are three ways you can do that. You can take that object, wrap a lens around it that will crush that object into a very small ball, and however high the refractive index of that ball is, if it's small enough, you won't see it. You can alternatively design a lens with a cylindrical nature and squash that object into a line, a very, very thin wire. And again, if the wire is sufficiently thin, you won't see it. There's a third way you can make something vanish, and that's to squash it flat. And I think you get the picture. It's each case, the cloak's got a different dimension. However, if you squash something flat and it has a very high refractive index, which it does, because as I explained, when you squash something, you increase the epsilon and mu in the plane parallel to the squashing direction, then although it's very thin, you can see it. It's a very flat mirror. So why would we do that? And it turns out that each of these three ways of hiding something becomes progressively easier. And to make this flat cloak, in which you make something appear as a very thin mirror, is actually the easiest to do, and it's non-singular, and there's a possibility that you can do it for optical waves. But then you have the problem, how do you hide a mirror? Any ideas? If I put one mirror on another mirror, you just get the mirror back, okay? So you can hide a mirror by putting it on top of a mirror. You don't seem to believe me. Okay? And that's the idea of this, and it was why it was called hiding under the carpet, because the carpet is the, is the mirror, and if you squash an object flat and it's lying on a mirror or a ground plane, then it will vanish because it just looks like a flat mirror. So here's Jensen's, Jensen, by the way, is now working in Hong Kong at City University, and here's his design for a cloak in which he designed a quasi-conformal transformation. So he's taken the material of flat space and he's squashed it upwards in such a way that these little cells remain basically squares, almost. And that means that the thing stays isotropic. And that should be easier to build. I'll come to that later. And in that way, you've created a hidden space. And this whole thing, which is on a mirror, just now looks like a flat mirror when viewed from outside. And computer simulations confirm that. So here's the cloak wrapped around a hidden object here, which is a mirror which bulges out, leaving a space in which you can hide something. And you can see that you just get a single beam of light reflected from this. If you take the cloak away, simulations show that the two facets of the cloak send light off in two directions. So if I was shining a laser beam over that, I'll try not to hit anybody with this, there would be a twinkle in the laser beam as it went over this object because it would split into two at this point. And you very easily detect it. But the cloak stops that from happening. Now, Jensen cleared off to Berkeley, where he got involved with some experiments, and the cloak was built. The way that was done was in silicon. So here is a silicon slab, and here's the start of the cloak. And the way the refractive index was varied was to make the simplest metamaterial you could imagine. So you can change the dielectric function of a material by drilling holes in it, by making it less dense. If the holes are very closely spaced, sub-wavelength, then it just looks like a homogenized system. And so this is a homogeneous system here, and inside here it's inhomogeneous with a gradient of epsilon according to the prescription for the carpet cloak. And you can see there are less holes here, so it's more refracting, and more holes here. So it's less refracting in this region here. And here is the cloaked area, and a silver mirror was put over the whole thing. Now, here's, I think this is an electron micrograph. It's the tiniest cloak you could imagine. This is 1 micron. So it's just a few microns across. And you can see that these holes have been drilled in the silicon by a focused ion beam, and they have the density as prescribed. And here's a little tunnel, which is being hidden. Here are some experiments. So, Jensen, which of the experiments, are they on the left or the right? Can you remember? On the left? Yes, thank you. So here are the experiments. They look so alike. And here's a Gaussian beam. It's hitting a mirror. And of course, it just reflects a Gaussian beam. So that's what a trace, the experimental trace, looks like. You then make a bump on the surface of the mirror. And the facets of that bump scatter the light into several directions. So the beam breaks up. There's a twinkle as you pass the beam over that object. And now in the third picture, you put the cloak over the object, and both in the theory and the experiment, the beam is reunited again, so it just looks like a flat mirror, and you see this trace here. So that really very nicely confirmed the principle of the carpet cloak, and that you can cloak optical things, but you might say, well, that's very, very tiny. It's very impressive for a first optical cloaking experiment, but we'd like a big one, please. And that was actually achieved by Zhuang Zhang, who has recently moved to Birmingham University in the UK, and he collaborated with one of my students, Yu Liu, and they made a rather big invisibility cloak. And at the same time, there were experiments done in Singapore, but by these guys who had the same idea and came to very much the same conclusions. The disadvantage of this cloak is that it only works for one polarization of light. So what did they do that was different? Well, when Jensen designed his cloak, he thought he'd make it easier for the experimentalists by making the material in the cloak inhomogeneous, but isotropic. And it turns out that if you want to make a big cloak, it's actually easier to have something which is anisotropic, but homogeneous. And you can do that by a transformation in which you take every vertical line here and you compress it by the same factor. And so you get a cloak like this. But because you've only compressed in the vertical direction, you then have a material which is anisotropic. And if you choose the compression factor right, which is basically just choosing this angle here, then that material might be the naturally occurring mineral of calcite, which is naturally anisotropic. And in China, there are whacking great crystals of calcite available, which were obtained by Zhuangzhang through his Chinese contacts. And this is how the crystal was cut, with the optical axis at 30 degrees to the vertical. And so this calcite cloak should provide a hidden space so that now in this space here you could hide anything and it would still appear to be a flat mirror. Okay. Here's a ray tracing experiment which shows that, again, you get the beam splitting up if you don't cloak, but if you do cloak, you get a nice uniform beam refracted, whatever the angle of incidence, by the way. So to show what was happening, they had this rather neat demonstration. So they took the alphabet, mirror reversed, and then they reflected it off this mirror here. So if that mirror were flat, you should see the alphabet in the right order. But if there's a kink in the mirror, so you just have the tunnel but no cloak, then the alphabet has a gap in it. So you have A, B, C, D, R, S, T, U. So the middle bit of the alphabet is missing because you've got a kink in your mirror. And then the test is to put the cloak in place and see if the alphabet comes out right, A, B, C, D, E, F, G, H, I, J, K. So the alphabet looks as though it's viewed through a flat mirror. It's done exactly the right job. And by the way, this is not false color. This is white light. And the guys use white light to show that it's a broadband cloak. And you can see there's a little color fringing there. There's a little bit of chromatic aberration, but not much. This works for the entire visible spectrum, and so it's a broadband cloak. But it only works for one polarization. So a lot of progress there for visible cloaks using this idea of a carpet cloak. Now, I made a big deal about cloaking the near field or controlling the near field because many of those cloaks which I've described before could have been designed using ray optics if you'd have fooled around enough with them. But what you can't do with ray optics is to control static magnetic fields. So that's the big challenge. So now I'm going to show you some work on cloaking a static magnetic field, and we're actually manipulating the field lines of the magnetic field. And this is done using, I should first of all acknowledge Ben Wood and also my experimental colleagues at Imperial who've actually done some experiments on this. And the idea there was to produce an anisotropic magnetic material. Now, there is an issue here because when you make the cloak, you compress that material. And if you remember that law I gave you, in the direction perpendicular to the compression, the mu has to increase. Only mu matters because it's a static magnetic field. Mu increases. That's okay because you have ferrites which have a mu much greater than 1. But there's an issue here because along the direction of compression, the law says that mu has to decrease. And although you have diamagnetic materials, the diamagnetism is typically very, very weak indeed. So what you need to do is to design a material which is very, very strongly diamagnetic by a factor of 2 or 3 or so in one axis only and anisotropic. And the way we did that was to take some lattice of superconducting plates. Now, if you imagine a magnetic field parallel to the plates, because the plates are taken to be very thin, the magnetic field can travel along that direction and really not have its progress interrupted at all by the superconducting plates. It just ignores them and goes parallel to them, as the rule of superconductors say it should. So mu in this direction is not altered. But perpendicular to the plates, something dramatic happens because the magnetic field lines can't penetrate very far at all into a superconductor. It's the Meissner effects. Magnetic fields were expelled from superconductors, and therefore the magnetic field has to squeeze into this gap here. Okay, spread out a little bit, squeeze into the next gap. So it's got to do this motion like this. And it turns out that if you calculate what the average fields are due to that effect, it actually reduces the mu in this direction by quite a strong factor. Now, our experimentalists built that structure. The way they did it was to take a microscope slide to deposit a thin layer of lead on it, and then to scribe the lead to make these gaps here. And then they cool the thing down to helium temperatures to make the lead superconducting. So that's how it was realized. And you can do some very simple theory which predicts, now let me see, so this is 9 layers of superconducting material. The side of the square was 133 units. Not quite sure what those were. They certainly weren't millimeters. And the spacing between the plates was 34 units. And as you decrease this spacing, you're more and more squashing the magnetic field in there, and so you're reducing the permeability. And so we really got some of the most extreme diamagnetism that you can imagine here. This is 4 or 5 times less magnetic than the vacuum. And here's the permeability which was measured. And you see, except for this very extreme value here, there's really quite good agreement between theory and experiment. However, we weren't able to persuade our experimentalists to go on and build a full cloak, though we'd designed one for them. Here are the superconducting plates. They reduce mu in this direction. Here is some ferromagnetic material, which increases mu in the radial direction. So this is really just the same cloak that you would use for radar waves, except that it's only acting on on a static magnetic field, so there's no electric component to this cloak because it's not needed. And there the matter rested for some time until last year, when a group at Harvard, these people here, published a paper in Advanced Materials. They didn't tell me about it, so somewhat later that I realized. So here they've built some diamagnetic material, made as we did, out of lead, which has been scribed, and then filled in with chromium, which is a magnetic material, to give the parallel component of the fields, of the view. And there is the cloaked region here, and the magnetic field is generated by 2 solenoids either side of it. And they're going to show experiments for 3 different sorts of cloak. So they're going to make a measurement here at the center of the cloak. So when you put the cloak in place, the field should vanish here. And if it's a real cloak doesn't disturb the fields outside either. Now, you might say, well, why on earth would you design a magnetic cloak? Because you can exclude magnetic fields in other ways. You can take some mu metal, which is a very highly permeable metal, wrap it around the object. The mu metal grabs the magnetic field and excludes it from the inner region. Or you could take another approach and say, well, why don't we do the opposite thing? Why don't we wrap a superconductor around, and then the superconductor would simply repel the magnetic fields, and again, that would reduce the field inside the cloak to 0. But both these approaches have one disadvantage, and it is that the magnetic field outside the cloak is highly disrupted. It produces a very, very strong dipole moment on the screening substance, and that would produce a strong force. So, for example, if you're in an MRI lab with very powerful DC magnetic fields, and you were trying to screen those fields with this method, the fields will be highly disrupted outside the magnet. And you rely on the uniformity of these fields for the precision of the MRI experiment. And therefore, both these methods of cloaking are not acceptable in some environments. Whereas the function of a cloak, a true cloak, is not that you should not know that it's doing its job of cloaking. The field should be undisturbed, and therefore the forces on the cloak itself should be 0. So here are the experiments by the Harvard group. The first one is simply a solid superconducting shield. And here are the measurements on sensor 1. And you see that if there's no shield, then as the current in the solenoid increases, the field increases. When there's no shield, of course, that's what you'd expect. But if you put the superconductor in place, there's absolutely no response. So it's doing its job of shielding, but it's not cloaking, as the next slide shows, because here we're doing a measurement outside the cloak at this point, and you can see that when there's a shield in place and no shield, the fields are different, so you've actually disrupted the field outside here, and that's obvious if you just trace the field lines. Now, the second experiment is using mu metal, and that shields the inner region, but in a different way from the superconductor. Now the shield is grabbing the field lines and making sure they don't get to this region here. But again, you see the disruption. And once more, the 2 measurements show that inside, shielding is occurring, no field when the shield's in place. But external to the shield, you can see that again, there's a strong dipole field generated. But but notice in the opposite direction, because this is expelling the field and this is attracting the field. But it's not doing a cloaking job, it's just a shielding job. And finally, they produced, I thought this was a really beautiful experiment. So this is the cloak using the superconducting squares and the chromium ferromagnetic, and this should be leaving the fields undisturbed, as in a true cloak. And again, the sensor inside shows that there's shielding going on, as before, perfect shielding. But in contrast to 2 other measurements, we see that the field outside here, and they actually took measurements at several points around here. I just show 1 at sensor 2. The data lie on top of one another and very, very beautifully screened in this way. Okay, so that's the end of the first section on transformation optics and cloaking. And I've shown you the concepts of transformation optics there, and I've guided them from the original experiments, which were essentially just steering rays around an object, and gradually shown you how you could alter the scale of that going inside the wavelength. And those final experiments were actually controlling the near field, controlling a pure magnetic field, something which we did not have the technology to do before transformation optics. So now I want to concentrate on that theme, and if I can, oh, wow. Okay. Could you get my second talk up, please? Yeah, that's the one. Okay. And talk about how we can control the near field in optics. So we control the near field for a static magnetic field. And here what I want to look at is what happens to the electric near field when we look at sub-wavelength systems. And the issue I want to address here is how do we control light on a sub-wavelength scale? And the challenge, which I'm sure you all know about, is that if you just use conventional lenses, then you can't get the resolution of an image to better than some finite fraction of a wavelength. But by using materials with negative parameters, I showed a long time ago in 2000 that you can, in principle, design a lens whose focus is not limited by the wavelength. But here I don't want to talk about making images. I want to solve a simpler problem, and one which, therefore, will be closer to producing practical devices. And I want to talk about harvesting light. And that's a simpler challenge than focusing light. If you have a lens which focuses light, then every point in the object has a corresponding point in the image. If you harvest light, that's a very different challenge. What you want to do there is to take every incoming beam of light and concentrate it to the same point. So you might want to do this if you want to force photons to interact with one another. Nonlinearities in optics are very weak, so you normally need very powerful lasers to get strong nonlinear effects, particularly if you want nonlinear effects which are fast and operate on the same time scale as the frequency of the light itself. You may want to do spectroscopy. There's a lot of talk about doing single molecule sensitivity, and to do that, you have to bring the light onto the same length scale as the molecule, so you have a chance that one molecule will catch one photon, okay? If you can only concentrate a photon into a square micron, and an atom has a cross-section of a square nanometer, then the chances of them interacting are rather small. So you've got to get the light onto the same length scale as the atom or molecule in order to have that sensitivity to a single molecule. You might want to enhance the efficiency of solar cells. You might want to improve the efficiency of lasers and to make lasers on the nanoscale, and people are doing that already. Rupert Holton in our laboratory has a nanolaser. But the same wavelength restrictions apply to harvesting as apply to focusing. And so we're going to use the same tricks of negative refraction, or at least negative epsilon, to achieve that. So here's the sort of experiment you might think of doing. So you might have some plasmonic system which would harvest incoming beams, and you might have some nonlinear material placed at the point where the light is concentrated. The photons talk to one another here, and so they might exchange some energy, for example, and come out mixed. And you'd really, to exploit this to its full potential, you want this system not just to operate at one frequency, you want it to be broadband, and that's quite a challenge. Of course, normally you would do this with a single resonance, but a resonance tends to be narrow band, so you have to think about the ways of doing this. So the way we start is to say, well, let's start with the spectroscopic properties. Never mind about the geometry. Let's get the spectroscopy right. So let's find a system which collects light from an atom or molecule. It's a broadband system. And ideally, we would like to be able to solve it analytically because computers find it challenging to address the different length scales you will get in this problem. But it may not have the right shape. The geometry may be wrong. But we can fix that because we know, having found one system, that we can transform it using transformation optics to a whole set of systems with a different geometry. And then use transformation optics to calculate the properties of the transformed system. And the spectroscopy doesn't change, but the daughters inherit all the analytical structure of the mother system. And so the whole family of structures can be derived from transformation optics, containing the same analytic genes, if you like, but with widely different shapes and sizes. So just remind you of this transformation optics. And I make an observation here that if all your fields in 2 dimensions and you make what's called a conformal transformation, so in a conformal transformation, if you squash a system this way, then you must also squash it in the orthogonal direction. So if you start with a little square, you can only change the size of that square. You can't change it from anything else than a square. But now, if you squash this way, you increase epsilon in this direction. And then if you squash this way by the same factor, you reduce it by the same factor. So conformal transformations in 2 dimensions have this delightful property that they don't change the material parameters. And that's really beautiful because you don't want to be hunting around for different materials, even with the flexibility of metamaterials, every time you do a transformation. So the archetypal system for making material for making plasmonic systems is silver. And if you make a 2-dimensional silver system and you make a conformal transformation of it, then it can still be made from silver. And that's a really, really nice result, I can tell you. So what are these systems that I'm referring to? So we want a broadband system. And typically, if you want something to be broadband, it has to be infinite, okay? Because that means a continuous spectrum. And only infinite systems, with some exceptions, which I'll come to, have a broadband structure. So typically, one might start with a slab of silver. Now, the surface of silver supports surface plasmons. And if you have a thin slab of silver, the surface plasmons talk to one another across the slab. And so the surface plasmon will now have some dispersion as a function of wave vector in this direction. And it turns out that the dispersion goes all the way from the isolated surface plasmon frequency right down to 0. So it's about as broadband as you can get. And furthermore, a similar system will be one where instead of having a slab of silver, you have a waveguide, a 2-dimensional waveguide cut inside silver. It has similarly a broadband spectrum. And if you put in this place here an excited atom, that atom might radiate, and much of that energy will be captured into the surface plasmons. And because they disperse, they have a finite group velocity, and so they will take the energy to infinity. So we're doing some of the right things here. We have a broadband spectrum. It can harvest light, capture light, and take it to another place. Unfortunately, that other place is infinity, and that doesn't amount to harvesting, does it? But we can fix that. So we make a conformal transformation, which can easily be done if we take z as the complex number x plus iy, as you will recognize, and we do an inversion. So this inversion maps points at infinity to points at the origin and points at the origin to infinity. And so in this case, the light goes to infinity. But now if we map infinity to the origin, this is the accumulation point of the light. And the harvesting point in the center here, I'm going to invert about the center of the dipole. So these become the remote parts of the silver, this bit here. So we get a system. Oh, and one more important thing. If you invert about the center of a dipole, you can think of a dipole as two very large charges very close together. If you then do an inversion about the center of the dipole, instead of being very close together, these charges are now very far apart, near infinity, in fact. And that produces a uniform electric field. Now, you don't have to produce that electric field by two charges in infinity. It could be an incident plane wave. And I'm going to work in the quasi-static approximation in which only the electric fields have to be considered. And that means that this whole system has got to be much less than a wavelength. So now we're mapped into a system where you have an external plane wave producing an electric field, a uniform electric field. The large bits of this system of cylinders harvest the light. It acts like a dipole antenna. And the radiation is gradually focused onto this spot here. And in an ideal system, just as these waves never reach infinity, these waves never reach the origin here. They go slower and slower. And because they go slower and slower, but carry the same energy, that energy has to be compressed into a smaller and smaller length. So the energy density rises. And in an ideal system without loss, you would find that the energy density would grow to infinity at this point here. It doesn't because of loss. Similar system can be achieved by inverting this one here. And in that case, instead of two cylinders kissing on the outside, you get two cylinders making a crescent like this. But the same principle applies with energy harvested here and focus this point here. It's a very beautiful system. And Ross McPheeder was the person who first educated me through his very early papers, I think in the 80s. Was it the 80s, Ross? Yeah. In which he pointed out that you could have a finite system which was singular, and the singularity is the kissing point here, which is singular and therefore had a continuous spectrum. So you can have a finite system with a continuous spectrum, but it has to be singular. So here are some plots made of a system which is illuminated with plane wave, and you can see that the electric field which is mapped here is being focused to this point here. The intensity increases greatly, but you can also see that the wavelength of the plasmon shortens as you compress everything. You compress the energy density, and you compress the wavelength as well. And that's very nicely illustrated by these wiggles getting closer and closer together here. This actually took into account of the loss of the silver, so there isn't an infinity here, but the intensity nevertheless gets very great. And here's the kissing cylinders with a similar picture. Perhaps we can illustrate that accumulation of energy more precisely by this graph here. So what we're plotting here is the electric field in the x direction as a function of angle. So 0 degrees start here, and as you go to 180 degrees, you're coming towards a singular point there. And as you compress the fields by this inversion procedure, you can see the wavelength getting shorter, but also the amplitude of the field, because of compression, also increases. And the blue curve is for the Johnson and Christie data for silver, and you can see that as you compress the energy, the electric field gets stronger, but then it collapses. And the reason for that is that as the wave goes slower and slower, it becomes more and more vulnerable to absorption. And silver is a very good conductor, but it does have an electrical resistance, and eventually that will win, and it will capture all the energy into heat loss. but not before the intensity, the amplitude of the electric field has risen by a factor of 1,000 over what it was in the incident plane wave. That's an energy density of 1,000,000 times what it was originally. If you're doing a Raman experiment, it's actually proportional to the 4th power of the field enhancement, and the Raman signal will be enhanced by 10 to the 12th if, in this particular system. So now I did want to show you something else here because it will be relevant in what I'm going to say in a few moments. You can, I'm not timed to show it, but you can generate from these very simple systems of waveguide, of a slab waveguide, by applying lots and lots of different transformations. You can generate a whole family of systems. And one of the things you can do is to make a sharp edge, for example, and see how the energy accumulates there. You can take 2 cylinders which are not actually touching, and then you get this spectrum here. And it illustrates very nicely that if you don't have a singular point, if the cylinders don't touch, then the continuous nature of the spectrum vanishes. So if you start with 2 cylinders far apart, you just get the cross-section of the cylinders, of the isolated cylinders here, which are at the surface plasmon frequency. And then as you bring the cylinders closer together, the levels hybridize, and but nevertheless the spectrum remains finite. It does spread out, and finally, when the cylinders touch, the spectrum, you can see the spectrum merging in a continuum here. Here's the separation of the cylinders plotted as a function, as a ratio to their diameters. And this is more or less what they look like. So you've got to get the cylinders very close before you get a broadband spectrum, and that will be an issue, as I'll show you in a moment. Now, there's something else that I'd like to mention here, and it's an issue that I would call hidden symmetry. If you want, you can say, well, I'm not particularly interested in doing analytic calculations. I have a big computer. I have some software that I can apply, ComSol, for example, and I can just give this to the computer and ask it, please, to tell me what the answer is. And indeed, we did check our analytic calculations in that fashion. And it will give you an answer. It really strains the computer because you have many length scales here, of course, because you have a very long wavelength here in the incident field, and you have a very short wavelength here at the plasma wavelength at the kissing point. So it's a difficult calculation, but you can do it. But you miss something, because what comes out of here is a very complex field, which are a mixture of many, many different angular momenta. And it's you say, oh, well, you know, it's complicated, but here's the answer. But I think you miss some understanding, because it was pointed out to me in Paris, actually, that in this system here, you have a lot more symmetry than in this system. So here you just have a mirror plane here, and that's it. So you have no conserved quantities here other than the mirror plane symmetry. But here, this system is translationally invariant. So all the states of this system can be classified by a wave vector. And because the states of this system are daughter systems of this one, so for every state you have here, you have a state of this system, which is just the transformed state. You can classify these systems by a block wave vector, even though this system has no block symmetry. So the analytic transformations can reveal structure in the fields which were not apparent to you just looking at this unsymmetrical system here. And hidden symmetry is very useful in understanding the character of all these states here, because each one, if they're viewed in the correct coordinate frame, has a block wave character, and it's not just a mess of angular momenta. What next? Oh, yes. Now, the analytic theory is exact in the quasi-static approximation for two-dimensional systems such as cylinders, but you can, especially in this region of the touching point here, extend the theory approximately but very accurately to cylinders. And Antonio Fernandez Dominguez has been the moving spirit of this in our labs in London. And he shows a very similar picture that if you illuminate a pair of kissing spheres, then this blue curve here, which is for the Johnson and Christie parameters for silver, show the enhancement as a function of angle. And if you come around to the kissing point, you get this huge accumulation of fields. But I want to draw your attention to the scale here, because the scale for cylinders showed an enhancement of a factor of 1,000. Here you're getting an enhancement of almost 100,000 for the spheres. And the reason for that is geometrical. So for the cylinders, you're gathering energy here, and then you're squashing it into this crack between the two cylinders. But you're only squashing in one dimension, okay? If you have two spheres which are kissing, you're squashing in this direction, in that direction. So there's a double compression going on. You get a double dip here. You get much more compression between two spheres if you push something between them than if you just take two cylinders. So the enhancements here are absolutely phenomenal. A 10 to the 5th enhancement will give you a Raman enhancement of 10 to the 20th. It doesn't happen, as I'll explain in a moment, but if you take this model of the dielectric function and perfect spheres, then you should get really phenomenal enhancements. But I'm going to steal some of David's thunder here. He's going to show you some more advanced experiments later. But these theories are becoming very relevant now, because people have known about these enhancements for a long time, perhaps not in such analytic detail, but it's been known that there's been giant Raman resonances for a long time. But what's been missing has been quantitative experiments in which you could take very flat surfaces, very spherical gold particles, and separate them by a known distance. Now, David's group, in collaboration with our chemists, achieved this. And the chemists contributed these molecules which go down either in a monolayer, a bilayer, or a trilayer. And therefore, if you float the gold on top of this, you know how many layers of the molecule you put down, and therefore you know the spacing between the sphere and the film. And if you embed some Raman-active molecules here, you can actually measure the enhancement of the signal. And that's what was done some time ago now. And here's the gap distance in nanometers. Notice that you don't really see these strong effects until you close that distance to just a few nanometers. But you can see that the SIRS Raman intensity enhancement is already headed up to 10 to the 4th here. It's not the millions I spoke of, but then again, you're not at the distance I've been speaking here. This is the nearest measurement is about 2 nanometers, and we really need you to go into a few angstroms to see the very highest enhancements. But nevertheless, it does show that the simulated data and the experiment are now coming together very nicely, holding out the prospect of harvesting and all these nonlinear things that I spoke about a moment ago. So, yes, I mean, you can do all these things. It's broadband, so you can do multi-frequency. You can, in one system, detect a wide range of molecules. You can do things like pump a laser at one frequency and amplify a signal at another frequency, nonlinear effects, and so on. Wonderful, but what can go wrong? Now, what doesn't go wrong is the resistive loss of the metal. Now, some of you may be familiar with the theory of the perfect lens, the so-called perfect lens, and there the killer, which stops you being absolutely perfect, is the loss in the metal. And if you can get the loss down, then you can get better resolution, or more nearly a perfect lens. But it's the loss that is the issue. But here, if you only consider loss as the mechanism stopping you getting to your goal, you can still, in theory, get enhancements of millions, billions even, and that's enough for doing very, very many more things than we can do at the moment. So loss is not an issue, because, but there are other things which stop you getting there. The first you might consider is the radiative loss. Now that increases with system size. So if you make a very large system, if the radii of the cylinders of the sphere is of the order of the wavelength, then what happens is that that's effectively a scatterer, and most of the radiation never gets into that crack. It's just scattered away by the dipole response of that system. And that kicks in when the system is of the order of the fraction, some finite fraction of the wavelength. So you really want to keep your system as small as you can if you're going to capture the radiation rather than just scatter it. Of course, there are problems of nanoscale manufacture. Making flat gold surfaces is not a trivial exercise. There are techniques such as surfactants that can make it less bad, but roughness of metal surfaces is an issue, as is manufacturing perfect spheres. So that's an issue. But this last one is really important, and it has to do with non-locality. What is non-locality? Well, let me explain it intuitively first. When you put an electric field on the surface of a metal, the field doesn't go into the metal very far. It's screened. And there's a screening charge which sits on the surface of the metal, and that produces a cancelling field inside the metal. So that's how metals screen electric fields. Now, in optics, we usually assume that that screening charge is an infinitely thin sheet of charge, and it isn't, because you can't compress electrons into an infinitely thin sheet. The most you can compress them is something of the order of the Fermi wavelength. That's very small. It's about an angstrom typically in gold, maybe a little bit more. And you may think an angstrom is a very small number and you can ignore it. But remember, to get these very strong effects, we have to approach these surfaces to within a few angstroms. So it really matters that the charge is not a perfectly flat sheet. And that's accounted for in the dielectric function as follows. That normally the longitudinal response to an electric field is considered to be independent of the wave vector of the exciting field. But non-locality says that that's not right, and there's a model called the hydrodynamic model which introduces dispersion as a function of wave vector. And what this manifests itself is that the bulk plasmon, which we normally assume in optics to not disperse with wave vector, actually does. So the zeros of this function, which give the bulk plasmon, they disperse with wave vector. And when you're below the plasma frequency, this means that the charge, which is carried by the longitudinal plasmon, does not decay instantly. It has a finite penetration depth. So there are actually two penetration depths here below the plasma frequency into a metal. One is the penetration of the electric field, and that's determined by the decay of longitudinal waves, and the transverse waves, and is dictated by the transverse epsilon. And the decay of the charge is dictated by the decay of the bulk plasmon. And you can take account of this by this dispersion factor beta here, which is related to the penetration of the charge. And that's going to remove these singularities. So now when we have two kissing cylinders or spheres, we assumed that the charge distributions actually touched at that point. And that's what's giving you this singularity, which Ross observed many years ago now, and gives you the continuous spectrum. But if the charge doesn't touch because it's a bit fuzzy, then you're back to having a discrete spectrum again, and the enhancement doesn't go quite the way you think it does. What happens, in fact, is that if the charge was confined exactly to the surface here, as these waves propagated inwards, they would never get to this point here because they'd have to squeeze into an infinitely thin piece of material. So they never get past this point here. But if the charge now becomes fuzzy, these waves can circulate around here. And so they can get past this point. And as they circulate, because the phase has to match here, they're actually quantized. And so I'll show you that now. So we make the transformation back to the system which we can solve analytically. It's a little bit complicated because the scale of the non-locality is altered by the transformation, but we can handle that. And again, Antonio was the wizard who solved much of this stuff and showed that the spectra are no longer continuous. But more important, the enhancement is reduced in the vicinity of the touching point. And this effect grows larger as the overall size of the system shrinks. And you can imagine why that would be so, because if you had a very big system, you wouldn't notice that you've got this non-locality here. But as the system shrinks, the non-locality doesn't shrink, and eventually becomes more significant compared with the overall dimensions of the system. Here are some absorption spectra calculated as a function of frequency. And the gray line shows the absorption calculated in a local model when you have the singular point here and the spectrum is continuous. If you then introduce non-locality at various degrees, blue, green, red, more and more non-locality, then you can see that the spectrum divides up into a series of peaks, which are more widely spaced the more non-locality you have. The green curve corresponds to the non-locality, which we think is observed in silver. In fact, we know is observed in silver. And so if you want to optimize the cross-section, you're caught between the devil and the deep blue sea. If you make your system very big, then non-locality doesn't matter, but the radiative losses catch you. The energy is scattered away instead of being harvested. If you make the system too small, the non-locality is very significant, and you don't get this collision of the energy at the touching point, and somewhere in between is a sweet spot. So what we have here is the enhancement of the electric field, plot as a function of frequency, and as a function of the radius of the touching, are they cylinders? Yes, touching cylinders. And you can see that in this lowest branch here, there's a sweet spot here at about 50 nanometers, something like that, where you're not got so much radiative losses, and the non-locality isn't killing you as it does at very, very small radii. So our recommendation is that if you're looking for big enhancements, then you look for system sizes in the range 35 to 80 millimeters across. Now, there are some further data which are going to be reported by David Smith. I'll skip over some of the details here, but because David is going to be talking about them. But what's shown here are data in which you now take a gold sphere above a gold surface, but now David can bring it in to distances much less than a nanometer. This is a log scale, 10 nanometers, 1 nanometer. So here, that's 10 angstroms, by the way. And I remind you all that a gold atom is about 2 angstroms across. Okay, so that's a gold atom down there. And here are experimental data showing the wavelength of that lowest resonance. And as you bring the systems closer together, that wavelength is redshifted to longer wavelengths. If you take a local model, that shift is far greater. And the reason for that is that you're actually making these charge distributions touch now, because they're not in the local theory, they're actually a delta function. But in the non-local theory, the charge fuzzes out, and you do not get quite such a big shift. And if you take the non-local parameters appropriate to gold, as given by the hydrodynamic model, then the experiments show that this correctly accounts for this shift here. So that's good news, because we want to be able to describe these systems in terms of the parameters which go into Maxwell's equations, epsilon and mu. If we can't do that, we're in trouble, because the alternative is to go to a full electronic structure calculation in which you take account of the detailed electronic structure of gold. And you can only do that for clusters which have a few hundred atoms in them. They're very small clusters, much smaller than those which we can control. And if you wanted to look at a system which was, say, 50 nanometers across, the chances of doing electronic structure calculation for that in the near future are virtually zero. So it's very important that we actually refine our model of epsilon. A local epsilon is not adequate. It won't describe these systems, and these experiments here show you, the experimental data tell you just that. There's a big discrepancy between the frequencies predicted by a local model and this non-local model. The good news is that this non-local extension of the dielectric function appears to take account of these effects in a macroscopic model. You don't have to go to the detailed electronics, and that's good news. I should mention that there is some debate about this. Excuse me. There's a competing theory which says that, yes, these effects are there. Things happen when spheres become very close. But one of the things that happens is non-locality. But the other thing that happens is that electrons can actually jump from one sphere to another, because when you bring two metal surfaces close together, the electron wave functions not only are diffuse inside, they spill outside as well. And you get electron tunneling from one sphere to another. And that is being investigated by Peter Nordlander and Javier Ispurua in San Sebastian. And they can account for their data with a tunneling model. We can account for our data with a non-local model. So watch this space. There's going to be some interesting debate about, is it all tunneling? Is it all non-locality? Or is it really a mixture of the two? I put my money on a mixture of the two. But it might be that in one regime of spacing, non-locality is the dominant one. Obviously, when the spheres actually do touch, then the tunneling is going to be very strong there. So it's going to be some mixture of the two. So at that point, you have to wait for David's talk to hear the details of those experiments. And I'm going to conclude there and call for questions at this point. Thank you very much.
Okay, thank you very much for a very instructive tutorial, as it should be. And as John said, this session is now open for some questions.
Is there any example of a structure with a continuous spectrum, but without structure singularity, like a kissing point or something?
With a continuous spectrum?
Right, with a continuous spectrum, but without structural singularity, like a kissing point.
No, you cannot get a continuous spectrum without a singularity. And the way to see that is that the singularities can all be thought of as essentially trying to compress infinity into a point. Okay. And the infinite system has the continuous spectrum. So if you don't have an infinity in there somewhere, either hidden or a real one. In the case of an infinite system, then you don't get the singularity. I think that's right, isn't it, Ross? Yep. You're the expert. Yes. Yep. Okay. Thank you.
Okay, we have one question from Roberto.
I haven't followed up what has happened with surface enhancement and scattering in the last several years, but somehow I remember people reporting enhancements of 10 to the 12.
They do, yes. And Fleischmann, of course, was one of the early people in that game, which is... but the problem is that the enhancements were not reproducible. The original surfaces were rough silver surfaces, and sometimes they gave it, sometimes they didn't. And indeed, because the geometric parameters were not known, they were just random assembly of roughness of the surface. There was a huge argument, which still rumbles on in some circumstances, about whether the mechanism was purely electrodynamic or whether it was a chemical effect which was going on. That started to be settled when a postdoc of mine did some calculations in the 80s showing that if you had these singular surfaces, you could get the spectacular enhancements you needed. And it took a long time before the debate was ended.
Okay, from Dr. Jablonowicz.
So there are structures which capture electromagnetic energy from all directions and over a broadband, and they focus it down to a small spot. But it was really Heinrich Hertz who first came up with these types of structures. We call them antennas. And indeed, he concentrated the energy to such a degree that he was able to detect radio waves by making sparks. So he had enough concentration of energy that he could actually make little tiny sparks in that spacing. I think we can learn a lot from antennas and antenna theory this way. One of the things that we learned, although I think you emphasized, and by the way, I should mention, the touching cylinders is a respectable kind of antenna. Now, normally, if you go to electromagnetics experts, they will not use transformation optics to calculate the properties, but transformation optics is a very good way to calculate it. Now, a lot of the properties they sort of come out when you analyze it from the viewpoint of an antenna. So in terms of getting capacitance changes due to the Fermi-Thomas screening length, I think you emphasized that very correctly. However, it's also important to emphasize the resistive losses. Now, the resistive losses on the face of it will not affect the capacitance that much, but it'll make a big difference when you try to do something useful with the system. And one of the parameters that we assign to this is to say, oh, look, are the resistive losses smaller or larger than the radiation resistance? And radiation resistance is usually around 50 ohms. So that is it forms a kind of important crossover point that would be very useful to calculate. So I think in addition to the calculations you've told us, I'd love to see more about the resistive losses.
There they are.
I need ohms. I saw the R and I expected it in ohms, but it's in nanometers.
The same as 30 meters.
The resistive losses are included for the larger system. The resistive losses are included through the Johnson and Christie dielectric function of silver, and the radiative losses are included in the larger spheres there. So you can see that, as you say, the radiative losses are important for large spheres, but the resistive losses, although they do they are important to be there, they are not the limiting factor. It's the non-locality.
Well, they're the limiting factor for certain other processes. When you try to do something useful, they usually end up as the limiting factor. I think just as you have taken into account the non-locality of the real part of the dielectric constants, I think you also have to take into account the non-locality of the resistive losses. I wouldn't take the number straight out of Johnson and Christie. I would try to maybe anticipate what effect, for example, surface collisions would have on the net resistance. Unfortunately, these things do cause a severe limitation when you try to use.
Well, we do know how much those collisions do affect things. It's thought that, let me first say that the DC resistivity in which the surface collisions and the phonon loss scattering is important is totally irrelevant to the optical response. If you cool copper from room temperature to liquid nitrogen, the DC resistance decreases by a factor of 100. Virtually nothing happens to the optical response. So what I call the static scattering is the dynamic scattering which is important, and therefore surface losses are not a big deal in my opinion if you have a flat surface. Now let me come to your other point that all this was anticipated by Hertz. Indeed, Hertz did concentrate fields, but there are two very distinct mechanisms here. The Hertzian method was to take essentially a conductor and short circuit the electric field in the vacuum. And so a field which was gathered over one wavelength was concentrated in a gap which was 1 millimeter. And that's called voltage division, and is a very common effect. And typically you get a factor of, well, the ratio of what, a meter to a millimeter for that. But this is a very different mechanism. You're not dividing the voltage. You're taking a wave and you're making it compressed as a wave, which can have a very much greater effect. So it's a very distinct mechanism. It achieves some of the same effects, but it's very different here. It's not voltage division.
And another question.
There is another effect in this non-locality, which I think was considered by Lipps in the 80s and 90s, which is the polarization of the core electrons, of the d bands, and this is important in noble metals because that breaks down the plasma energy a lot. So I'm not aware that this is included in the calculations that have been reported in the last few years, including yours and in Norlander's group. And
that's exactly right.
Our calculations. And I think this is an important issue precisely when there are small distances in which the electrons that are spilling out of the surface, and this spill out, whether it can be, has to or needs to be described quantum mechanically or classically or how it is, then one important issue is precisely that these electrons that are outside the surface, they are not screened by the d bands. So in junctions like between cesium or aluminum, that's not important because there are not such bands to screen, but in gold and silver it should be very important. What do you think?
Well, I think we're in an unknown territory, really. We have this hydrodynamic model for the non-locality. We're developing a model for the tunneling effect with the direct electron transfer. But one thing's for sure, that we're in deep trouble if every time we want to understand the electrodynamics of these systems, we have to do an electronic structure calculation. So somehow we've got to come to a way, just as Maxwell in the early days summarized the response of a bunch of atoms as a dielectric function. So we have to parameterize in terms of a model which we can actually solve on a macroscopic scale. I agree with you that there are all these effects. I mean, we share a common background in electronic structure, so we know the complications that can arise there. But somehow we've got to find a way of putting these all in a black box and presenting them to not just analytic theory, but to computers as well. Because computers can't macroscopically solve everything for a big system in a model which accurately describes electrodynamics. And that's the challenge facing us for plasmonic systems. I agree, it's not sorted.
Okay, I think if there's no more questions, we can thank John again for a very instructive tutorial.